Hello, stats students. I'm going to mention using your calculator a lot in this video. If you need a tutorial about how to enter things in your calculator, there will be an auxiliary video called How to Use Your Calculator, Part 1, that you can use to help you learn how to type this stuff in the calculator. For the purposes of this video, though, I'm just going to say, use the calculator, and then you get this answer, to save time on this particular video so we can get down to the actual content of this section. Last section in 6.1, we talked about discrete and continuous variables and how to calculate different probabilities with them. Sometimes, though, we need to convert the units of these random variables. For example, we might need to add 5, or we might need to multiply by 2. And so we're going to investigate how that affects the mean and the standard deviation of these random variables. We're going to be using the same example throughout this whole video, El Dorado Community College. In order to be full-time at El Dorado Community College, they need to be taking somewhere between 12 and 18 units. The number of units that a randomly selected student is taking has the following distribution. So they could take anywhere from 12 to 18, and those are the probabilities that they take them. And so we're going to use the calculator to calculate the mean and standard deviation of x. So I would type this into L1 and L2 and do one variable stats. And so when I do that, I get x bar equals 14.65. The notation you might see is mu of x, not x bar, mu of x. And we're going to interpret that. A randomly selected college student from El Dorado is expected to take about 14.65 units. And we can also get the standard deviation from our one variable stats. 2.056 is the standard deviation. The number of credits a student takes typically varies from expected by about 2.056 units. And so let's say it costs $50 per unit a student takes, and that determines their tuition. So you could figure out the average tuition also by multiplying the average number of units they take by 50. And so that's what this second table does, is they multiply everything in the first row by 50. I didn't multiply the probabilities by 50 because it's still the same probability of taking those number of units. And so then now it's the probability that you have some tuition. So now our variable is t. And so I'll replace list 1 with the new list 1 of the tuition instead of the number of units. And when I do one variable stats with this new list, I get the mean of t is going to be 732.5. So a randomly selected student oops, that's not an S. I'm going to say for a randomly selected student, it is expected, or the amount they expected tuition amount is about $732.50. And I'll get the standard deviation from my one variable stats as well, 102.8. The tuition cost typically varies from expected by about 102.80. And so notice how both the mean and the standard deviation changed when we multiplied by 50. So multiplying and dividing, it affects both the mean and the standard deviation. So now let's investigate what the effect of adding and subtracting has on the mean and the standard deviation. So in addition to their tuition charge of $50 per semester or per credit, they're also charged $100 per semester. And so we'll multiply by 50 like we did before, and then we add 100. So now we've got the overall cost is $100 plus the tuition that we got in the previous section. So the overall cost, now we have L1 and L2, where we took every tuition amount and added 100 to it. You can flip back to the previous table and see how we just added 100. Again, probabilities don't change. We'll run the one variable stats again, and we'll get the mean of C now. The mean of the random variable C is 832.50. And so the overall cost for a randomly selected student STU is expected to be about $832.50. And we can get the standard deviation from our one variable stats as well, 102.84. The overall cost for a randomly selected student typically varies from expected by about 102.84. Now it looks like I've rounded a little bit differently for my standard deviation between this example and the previous example, so let's ignore that 0.04 difference. The effect of adding or subtracting to a random variable only affects the mean. So the mean changes, but notice how the standard deviation stays the same. So especially if you don't have all the data, you only have the mean and standard deviation, you can apply these changes to the mean and standard deviation based on the type of transformation they want to make. Could be changing units from inches to feet, for example, and that will save you some time if you know these rules. And so in general, a linear transformation can be written like y equals a plus bx, where this is adding or subtracting with a random variable. In this case, the random variable is x, and b would be multiplying or dividing by a random variable. So to recap, a will affect only the mean. B will affect both. And so one thing I want to point out is if you're talking about describing the distribution, we've described the center and we've described the spread. The shape of the distribution never changes. So if it's skewed right, even if you add 5 to every number, it's still going to be skewed right. Okay, so let's look at one more example here. In a large intro stat class, the distribution of x, which is the raw score on a test, is normally distributed with a mean of 17.2 and a standard deviation of 3.8. So I'm going to label that. Mu of x is 17.2. Standard deviation of x is 3.8. The shape is approximately normal. We're going to define a variable y to be the scaled score of a student from this class. Now, the way they scale the score is they multiply by 4 and then add 10. So my new variable y is going to be, I'm going to multiply by 4 by my random variable x, and then I'm going to add 10. So the 4 will affect both the mean and the standard deviation. The 10 is only going to affect the mean. And so we've defined this variable, find the mean and standard deviation of y. So mu of y is going to be 4 times 17.2 plus 10, because the mean is affected by adding and multiplying, and I get 78.8. The standard deviation of y is 4 times 17, not 17.2, 4 times 3.8. And I don't add 10 for the standard deviation because that's not affected by adding and subtracting. And so I've got a new mean and a new standard deviation. And now we're going to calculate what is the probability that a randomly selected student has a scaled test score, so that's y, greater than 90. Now remember, the shape was approximately normal. That should have been your clue early on that we were going to be doing probabilities with normal CDF. So I'm going to draw the picture here. Greater than 90 somewhere over here. I'll use normal CDF from 90 to infinity, 78.8, 15.2. I'm using the mean and standard deviation from y. And when I do that, I get 0.23. And I need a sentence here, concluding sentence. The probability of a randomly selected student with a scaled test score greater than 90 is 0.23. So these are the rules for adding or multiplying by a constant, but sometimes I want to add two separate variables together. And so that has its own set of rules, which is what we're going to investigate now. If you go to the next page, you'll see that you have this whole long page to do one whole problem. For some reason, that was up at the top, but it should be about halfway down so you have room to write notes. So go about halfway down, and we're going to take notes on some of the rules for combining random variables. So far, all we've talked about is adding or subtracting, multiplying or dividing a constant, but now we're going to have two separate means and two separate standard deviations, and we're going to try to combine them. So adding variables. Let's say you're given two different variables, a and b, and I want to add the mean of variable a plus the mean of variable b. Then all I do is add the numbers together, and that gives me my total. You can just add the numbers together. So we're going to let we're going to let t be a random variable that is a sum of variable a and variable b. And so if I wanted to find the mean of t, then I would add the mean of a plus the mean of b. Now, if I want to find the standard deviation of t, it's not as easy. The standard deviation of t, you can't just add the standard deviations. you have to add the variances. So remember, a variance is the squared standard deviation. So you can add the variances and then take the square root and you're back at the standard deviation. So this is the formula for adding standard deviations. You add the variance of A plus the variance of B and take the square root and you'll have the standard deviation of the sum. So the reason you do that is, think about this like the distance formula. Remember, the definition of standard deviation is the average distance from the mean. So a standard deviation is a distance. If you add distances, or if you want to find the distance, you have to square the terms and then take the square root. So you think of the distance formula when you're doing this. Those are two endpoints and you're adding them together. Now, if you want to subtract random variables, let's create a new variable here. I'll call it D for difference. So we're going to let D be a random variable. It's not how you spell random. Random variable that is the difference between variable A and variable B. So the mean of the difference is just the difference of the means. Mean of A minus mean of B. Now think about distance formula again. You never subtract when you're doing the distance formula. You don't want to risk having a negative number under the square root. So the standard deviation, even though you're doing a difference, you're still going to add the variances. Notice how I'm still adding. So the standard deviation doesn't change whether you're adding or subtracting variables. But when you're adding or subtracting variables, the mean does change sign. You'll either add them or you'll subtract them. So these are the rules for combining random variables. And now we're going to look at an example using this. So go back up to the top of your page and let's read this scenario. Suppose that the height m, so we have one variable here, m, for male speed daters, follows a normal distribution, that's good news, with a mean of 68.5 and a standard deviation of 4. So let's record that real quick. The mean for males is 68.5 and the standard deviation for males is 4. And the height of females, we're going to use the letter F for female, follows a normal distribution as well, and it has a mean of 64 and a standard deviation of 3. So we have two separate variables here, male and female. So we want to figure out the probability. Let me change colors here. We want to figure out the probability that a randomly selected male is taller than a female. That's what we're trying to figure out. So I'm going to rewrite this probability so that I have a number that in mind, because you need a number in order to do normal CDF. I'm going to subtract females over to the left side. So now I have male minus female greater than 0. Well, this creates a new variable, males minus females. So I need a mean and I need a standard deviation for males minus females so that I can do normal CDF with those. Now keep in mind, if you add two normal distributions together, you'll still have a normal distribution, so don't forget about that. So the mean of male minus female is just going to be 68.5 minus 64, which is 4.5. And the standard deviation of males minus females is the square root of the sum of the squares. 4 squared plus 3 squared, which is 5. So we have a new mean and a new standard deviation. And we're trying to figure out when that's greater than 0. So I'm going to draw my curve with 4.5 in the middle. And we want to figure out when a male is taller than a female. So that means m minus f is greater than 0. So we'll do normal CDF from 0 to infinity. And I'm going to use 4.5 as the mean and 5 for the standard deviation. And when I do that, I get 0.816. So the probability that a randomly selected male speed dater is taller than a randomly selected female is 0.816. So if you're like an insecure guy, you'd probably feel comfortable going to this speed dating site because you'd have an 81% chance of being taller than the female. And if you're a female who only dates people taller than you, you'd probably be okay going here too because you have an 81% chance of the male that you date being taller than you. Let's look at a couple more examples on the next page. Suppose that a certain variety of apples have weights that are approximately normal, that's good news, with a mean of 9 ounces and a standard deviation of 1.5 ounces. So the mean of the apples, a bag of apples, just one apple, is 9 ounces. Standard deviation of that is 1.5. Bags of apples are filled by randomly selecting 12 apples. What is the probability that the sum of the 12 apples is less than 100 ounces? So we would pretty much expect 9 times 12 is 84. No, it's not. 9 times 12 is 108. That you'd get around 108 ounces per bag, but obviously apples vary in size, so you're not going to get exactly 108 ounces. So we're going to calculate a mean and a standard deviation of a bag of apples and then do this probability. So let's define a new variable. I'm going to let T be the total weight of a bag of apples. And since we have a new variable, we need a new mean and a new standard deviation. So the mean of T is going to be the sum of 12 apples. So 9 plus 9, and I'm going to do this 12 times. So really 12 times 9, which is 108. Standard deviation is going to be the square root of 1.5 squared plus 1.5 squared, so on, 12 times. Or you could just multiply that, 12 times 1.5 squared, and you get 5.2. So we have our new mean and our new standard deviation. We're trying to figure out the probability that a bag of apples is less than 100 ounces. So the total is less than 100 ounces. And so here's 108, somewhere in the middle of our curve. 100 would be over here, and it's less than 100. So we'll do normal CDF from negative infinity to 100 and use the mean 108 and standard deviation 5.2. When we type that into our calculator, we get 0.062. And all we need now is a concluding sentence. The probability a bag of apples weighs less than 100 ounces is about 0.062. There's going to be a follow-up video here to do the examples that are still in your notes packet, the StatsMedic examples. But here, this should give you enough practice so that you can do some of the homework book problems that I've assigned in your calendar, and ask me questions about them during my office hours, which are every day from 10 a.m. to 11 a.m. and 1 p.m. to 2 p.m. The Google Hangout link will be updated each time so that you can just click to join in and ask me any questions that you have about the problems you're doing. So make sure you look out for that second video with those examples worked out. And if you want the answers to the example below, go ahead and give it a try, and then I'll work that example out during one of the live office hours if you want to see if you got the answer right. So I hope you guys are having a good day at home, and look out for my next video.